Yay! Hello everyone, good morning. Thank you for being here. It's early. I am not normally awake this early on a Sunday. I don't know about you. Cool, so I'm going to talk to you about search engines. My name is Toria, and they gave me a whole hour to talk to you, and I will talk until they pry this microphone from my cold dead hands, so buckle up. We're going to cover a lot of material. I'm going to try to teach you everything I know about search engines. We'll start with an introduction to who I am and this problem that we're trying to solve. And then we'll talk about the problem, which is text search. We'll talk about the performance of text search and the quality of text search compared to trying to solve a problem with something naive like just a database. Then we're going to talk a little bit about ranking for relevance, and I'll explain what that means. We'll talk about open source tools so that if you should decide that you need or want a search engine for your project, you know what to do. And then we will recap and I'll take some questions. So part one, who is this lady? My name is Toria, I work for Shopify. You can find me on the internet at Scarlet Drive. It doesn't really mean anything, it's just two random words I picked. I tweet about technology, and after this talk, in a couple of hours, I will tweet these slides if you would like to see them again. So give me a follow there if you want to see some slides. I got a Bachelor of Computer Science from the University of Waterloo in 2010. That's 10 years ago. I'm an old lady. I've been reflecting a lot because it's the turn of the decade, and also Mayuko yesterday made me think about my life very deeply. So I've been thinking a lot about the turn of the decade and what I've accomplished in the last 10 years, and what I would say to myself 10 years ago. And I think 10 years ago, I actually kind of had it all figured out. I had a bunch of intern experience in my field. I had a job lined up full time. I've been cooking my own meals and paying my own bills. So I don't have for you any sage life advice. I assume you also have it figured out. What I would have liked to know 10 years ago that I know now is a specific technical thing, which is how search engines work. Have any of you, perchance, studied search engines in university? Phil. I talked to Phil about this. Cool. Some universities apparently offer classes on this. Mine did not. The field is often called information retrieval, so if you see a course called information retrieval, I'm going to give you an entire semester of information retrieval in the next approximately 40 minutes. Woo! Cool. So this isn't something I learned, but I did know a lot about databases, and that is going to become very relevant because I compare search engines to databases a lot. So story time. It's 5 years into my full-time career, it's 2015, and I've been working in New York City for the same company for those whole 5 years, and they were also my last two co-op employers. So that's a long time in our industry to stay in one place, and it was time for me to try something new. So I'm interviewing to work at this company, and one of my 1 hour interviews, the question was 2 words: design, search. Now, to be fair, I was applying to work on the search team, so that seemed like a fair question. I didn't know anything about search, really. But I did know that there was a thing called a search index. Just by pure luck, I had been given a task for 1 week at my last job during that 5 years. One time, I loaded a data set into something I knew was called a search index in order to create an autocomplete. So that you could start typing and it would auto-suggest for you what you might be looking for. So I knew that thing was called a search index, but I had no idea how it worked. I was just plug and play. But I did very deeply know about database indexes. I had taken an advanced level class in university on the internals of how databases work. You might know about this. There's a concept where you can put an index on a column in a database, and then it's super, super fast to search that column. So in this interview, I did no preparation whatsoever, and I'm database index, search index, probably the same thing. And they hired me. It worked. I fooled them. No, they hired me even though I was completely wrong. They are not the same thing. But it turns out that treating a search engine like a database will get you very far. At the end of the day, they're data stores. You put some collection of related documents in there. They conform to a schema. You add, delete, update those documents or items, and then you query them later, just like a database. So that was working really well. Until one day, a few months into the job, one of my coworkers is like, "Hey, can I get some help?" I'm like, "Heck yes, I'm very helpful." They said, "I want to add a new field to the search index. The field already exists in the database, but I want to make it also searchable and add it to the search backend. But I know," this is my colleague speaking, "I know that search engines are really, really high on disk usage and memory, So I want to make sure that I'm not going to overload your system when I add this new field. It's a big text field. Very nice of them to let me know. I had no idea how to help. I did know how much space a field takes up in the database. I knew nothing about how data was stored internally in the search engine, so I couldn't answer the question. It was time to buckle down and learn how search engines work. So, the problem that we're going to talk about to learn about search engines is text search. That's what search engines are primarily created and designed to solve. They do other stuff too, but we're going to talk only about text search today. So, we're going to imagine, for the sake of this conversation, that I have a website called Toria's Pet Emporium, where I sell clothing and accessories for pets. This is a real website. You can actually go to that URL on the bottom and you can pay these insane prices for these stupid pet-related products if you so choose. I made this store on Shopify. I'm an employee, so I can have like unlimited free Shopify stores. So I can do stupid stuff like this. I use something called drop shipping, so I don't manage the inventory or make them. I just charge an insane price for them, so I don't recommend that you buy these items, but you could. But for the purposes of this talk, let's pretend that I actually made this website from scratch myself, that I didn't use the Shopify platform. If I was making this website from scratch, I would probably make myself a database to track all the items I have for sale. I would give them each a title and a price, probably also some other stuff, a longer form description, a quantity, and then when they get inserted in the database, they get assigned a unique ID. Someone comes to my website, they want to buy something for their cat, they would probably do something like this. This is SQL, structured query language. I'm going to assume most of y'all know this. It's a really, really common way to query or interact with a relational database. The important part here is where title like %cat%. So like indicates we're going to do some kind of like regular expression matching rather than an exact lookup. And then the percentage symbols are our wildcards. So this says, give me everything you know about all of the items where cat is a substring of the title somewhere. So it finds our red cat mittens and our blue hat for cats and our cat hat. It also finds our vacation hat for dog because cat is a substring of vacation. It doesn't find item number 7, the kitten mittens. Arguably, if someone searched for cat-related items on my website, I want them to buy stuff. I want them to also see the kitten mittens. But let's assume for now that this is good enough. And we're going to say that this is an acceptable solution. The question that I want to ask is, how does it perform? Performance-wise, we have to scan the entire database, every item in the database, and then for each title string, we have to scan the entire string to confirm whether or not our substring is in there. So we have an n times m, where n is the number of items, and m is the length of the strings. Now, I'm so sorry for giving you big O while you're not in class. This is big O notation. For folks who don't know it, if you haven't learned this yet, or you're just like having, I don't know, PTSD looking at it, the short version is that big O is trying to describe the growth of an algorithm in the worst case, the upper bound of the growth of an algorithm in the worst case with respect to its input data. So m, the length of our strings, is fixed. We kind of throw that in the garbage. What matters here is the number of items in the database. And O of n means linear, so linear. Every time we have twice as much input data or twice as many items in the database, this algorithm gets twice as slow. In the grand scheme of algorithms, this is considered kind of okay. But in practical terms, if we have 10 or 100 or 1,000 items for sale, not so bad, computers are fast. We have 1 million or 10 million items in our database, all of a sudden, this takes actual seconds of clock time, depending on your server. You could always throw money at the problem and get a better server. Alternatively, we could make it faster. So we need to do better. Our users are not going to sit there and wait for like entire seconds for their results to come back. They're going to think our website is broken. This is bad. So the reason this is slow is that the data is not stored in any order that is meaningful to us. It's stored in ID order, and that's why we have to scan the entire database. Something you might know about databases is that if we did know the IDs of the items you were looking for, we could look them up super, super quickly. This would be effectively a constant time or like a single operation lookup. So you could kind of consider a database like a map from IDs to the other information about those items. What if we flipped it on its head, and instead we mapped from words or terms that we care about to sets of IDs of items that contain those words? This is the big reveal. If you remember one thing from today, let it be this: the inverted index is the fundamental data structure that supports all search engines. This is the magic. So one more time, we map from the words we might care about to the sets of IDs of the items that contain those words. Awesome. Now, someone comes to my website and they're looking for something for their cat. We can, in a single operation, find all of the cat-related items. We did it! O1, magical. If you're like, that seems too good to be true, you're pulling my leg, you're yanking my chain, you're right. First of all, we're assuming a perfect hash function. For folks who do know big O, the idea that a hash map lookup is O of 1 is just something we all like wink at each other and say is true. But like every interviewer or computer science professor I've had has like winked and said it was true, so we're all going to do that today. Number 2, we made some trade-offs. We don't get to delete the database after we create the inverted index. Don't delete your database, please. So we took up some extra storage. We now have 2 separate data stores that we need to keep. We also need to keep them in sync, which is actually a very complex problem. And finally, we had to do some pre-processing to actually create that inverted index, and I will show you in a little bit what that pre-processing looks like. And then finally, we haven't actually fully solved the problem. You see, I can't show someone on like my website, I found items 1, 3, and 5 for you. That doesn't mean anything to them. So we do still have to actually go back to the database and look up the information we know about items 1, 3, and 5, so we can show them that. So interestingly, we know that database lookups are really fast because we know the ID, but how many of them do we have to do? We have to do R of them, where R is the number of results that we found. So this is kind of interesting. Search engines scale query time not with respect to the size of the initial input data, but with respect to the number of the results that were found. Pretty weird. R is guaranteed to be less than or equal to n, the number of items, so we've certainly done no worse. But I think you can imagine how most of the time it would be a lot better. Furthermore, I propose that we never show people the complete results set. We have some fixed upper bound of items we actually put on a page. Like, if there were 10,000 cat-related items on my website, I wouldn't load all 10,000 of those items and their pictures and their full descriptions. That would be way too slow. I would cap it at some magic number like 25, and then I would give them some like user experience widget at the bottom that indicates you can keep scrolling to see more, or you can hit like a page next to see more. So in fact, magic, hand wave the O of 1, this reduces to O of 1. We did it! Search engines provide faster results than a database, specifically for the problem of text search. So we're actually now faster than a database, magically. Next problem. Let's review those quality issues that we saw before. First of all, we got this vacation hat for dogs. Someone searched for cats. It would be horribly offensive to show them dog-related content when they search for cats. Let's not do that. Additionally, I would really like, this is a customization I would like to make, I would really like searches for cat to return anything that also said kittens, please. And then finally, searching for cats with an S. We didn't talk about this one, but naively, if we just threw an S on there, someone searched for cats with an S, this would completely mess with our algorithm. All of a sudden, we would not find the red cat mittens or the cat hat because of that pesky S. Now, you might be thinking, but Toria, couldn't I write this statement where for every combination of cat or cats and kitten or kittens, I check for white space or punctuation on either side? Don't do this. This is terrible. Instead, what I'm going to show you is how the steps that we took to create the inverted index are going to magically fix all of these quality problems. AKA, we're going to first talk about how we did this. How do we actually build the inverted index? It's time. The answer is analysis. We have to analyze those text fields and do some stuff with them. We have to slice them and dice them. And specifically, we're going to do 2 things. We're going to tokenize them, and then we're going to normalize them. Normalizers are also known as filters, and you're going to provide some different combination of filters depending on what you want your website and your search to do. So first up is tokenization. Tokenization is, as it sounds, tokenizing your string into its separate component, tokens, terms, or words. In the English language, this is pretty simple. You can pretty much just tokenize on white space and call it a day. I think you can imagine, though, how this would be a lot more complicated in a language like Japanese or Chinese or even German, where we don't always actually have white space separating words and concepts inside of a longer phrase. But I will leave that for you to think about and Google at home later. So next up, our first and most common normalization phase is called stemming. So this is the process of converting every word to its root form. So plurals become singular, verbs take on their infinitive form. This is stemming. You can do stemming in two ways, dictionary-based or algorithmic. Dictionary-based is slightly more likely to be correct, but of course it takes up a huge amount of memory because we have to store the entire dictionary. So in fact, we typically use algorithmic stemming, and the most common English stemmer is called the Porter stemmer, and it's just like a series of hard-coded rules that work pretty well for English. We're going to apply some additional filters. Lowercase and character filters are also very common. So I think it's time for a note about what these filters are actually doing. Our goal here is to make the same concepts the exact same text in the backend. So for example, if I had an item for sale that was like a funny gag gift that's like a resume for your cat, and I'd spelled it correctly with the accent aigu, and then someone comes to my website and they search for resume without any accent aigu, maybe there's some naive American who doesn't know any better, sorry to the Americans in the room, I want them to still find my item, even though I put the accent aigu in there. So what we do is we convert any reference to resume either with or without the accent aigu into the same form in the backend. And you'll see in a little bit how this actually works with a practical example. One more similar one is synonym replacements, so different spellings or forms of the same word, abbreviations of a longer form word. We want to make these equivalent in the backend, so if you search for one, you find the other, and vice versa. The last filter that's really common to apply is the removal of stop words. Stop words are words that are really, really common in the language that you're using, so common that it would be effectively useless to bother trying to search on them. So you could imagine that if I had longer form descriptions of all of my items, almost every one of those item descriptions would say the somewhere in it. Then we have a bucket in our inverted index that says the and just has every ID number. That's a huge waste of space. It doesn't really add any value to our search, so we just cut these words out entirely. So let's look again at our quality problems and see how the analysis phase can solve them all super, super magically. So cat returned vacation time for dog. Using a small example, let's say we're just working with these two items. First we tokenize them, then we remove the stop words, and we end up with a little mini inverted index that looks like this. Someone comes to my website and searches for cat. Now, the cat bucket has only item 5 in it. This cat and vacation were tokenized into completely separate words or terms. So we've solved our first problem with tokenization. Next up, searching for cats with an S. That was problematic because it didn't return cat hat with the naive SQL solution. So again, small example, we tokenize, then we stem, then we remove stop words, and we end up with a tiny inverted index like this. Someone searches for cats. So, map lookups have to be exact matches. So this is a problem. The solution is that everything we did to all of the input strings when we created the inverted index, we do those same things in the same order to the user's input query. So what that looks like, and we do it secretly behind the scenes. So they typed cats with an S in the search box. We secretly behind the scenes remove the S, and then we know to look at the cat bucket. And we've solved our problem by stemming both the input data and the user's query. Problem number 2, solved. Problem number 3, and this is like my optional design decision, is that I would like a search for cat to return kitten mittens. So I think you can see where this is going. We're going to tokenize it, we're going to stem it, and then we're going to do a synonym swap. It doesn't really matter which one we do, but for argument's sake, let's say I convert every reference to kitten into the word cat. I have an inverted index that looks like this. Now, searches for cat return items for both cats and kittens. Similarly, searches for kitten, we're going to do a synonym swap, right? We're going to apply the same transformations, and we're going to find the cat bucket, even though they search for kitten, and we're going to return all of the items for both cats and kittens because of synonym swapping. So we did it. Search engines provide both faster and better quality result sets than just using a database specifically for the problem of text search. Now, let's revisit this question from my coworker. We've learned a little bit now about how inverted indexes or search engines store data internally using inverted indexes. So my coworker offers me some information that they think will be useful to me, which is the size of the field. We both know the size of the database. Let's imagine there's like 50 million items in there. But now, knowing what I know, I ask a follow-up question. I basically can't determine the size of the input without analyzing the data, or the size of the new field, of the inverted index, without analyzing the data that's going to be in those strings. So if it's like this is a user-submitted field that could have anything in it, huge problem for me. I have no idea how big it's going to be. Like for example, we had 8 rows and that became 8 rows. So we just happened to have a pretty good distribution of different terms, pretty much the same size. If we had 100 or 1,000 or 1,000,000 or 1,000,000,000 rows, and every single string only said good dog or bad dog, we would end up with an inverted index with only 3 rows. Pretty interesting. So my coworker says, well, yes, this is a fixed subset of possible strings. These are the categories, and I'm like, awesome. That means I can analyze those categories, and for example, if everything was either a pet accessory or a pet bed, I can say with confidence that I would have an inverted index with only 3 buckets. So I can now estimate the size pretty accurately. Hooray! You've earned this. Oh, thank you. This is, we're beyond the halfway point, and now I take a drink of water. These are my cats. Their names are Momo and Naga, and if you get that reference, you're cool. It's from Avatar: The Last Airbender. Cool. So we have covered text search and how text search is magically faster and better than using a database for the problem of text search. Now we're going to talk about relevance. Relevance means if there are, let's say there's like 50 million items on my store now, and 10,000 of them say cat in them, and we decided earlier that we're not going to show them 10,000 items, we're going to show them like 25-ish at a time. What are the first 25 I should show? What order should I rank them in? So typically the order that we display them in is called relevance order. When you go online shopping at like your Amazon, your eBays, like whatever website, typically that is the default sort order. It might say default, or it'll say best, or it'll say most relevant, but this is typically the default sort order, and then you can choose like, no, I would like to sort by price or alphabetically, but like 99% of the time the default sort order is relevance order. The most common way of doing relevance matching for text fields is called TFIDF, and I'm going to attempt to teach it to you now. So TFIDF stands for Term Frequency Inverse Document Frequency. Term frequency is the number of times this term appears in each document with respect to the total number of terms in the document. So what term frequency is trying to capture is for this particular search term, how relevant is each document to that term. Inverse document frequency is the natural log of the total number of documents over documents which contain this term. So what this actually means in English words is given a multi-term user input query, if they searched for like multiple different words, which words are the most important ones? And TFIDF posits that the words that are the most rare in the entire corpus of documents that we're searching are the most important ones. So we're going to give them a boost in the ranking. So let's look at what this really looks like. We're going to start with a single term query, so IDF is not going to matter at all. We're just going to look at TF, term frequency. So we're going to imagine that also on my website, I have like a microblog, you might call them tweets. I have these short little tweets, and someone searches for cat, and there's 3 tweets that say cat in them. The question is, what order do we display them in? Now you might think, naively, because you don't know what I know, that item number 3 should be first because it says cat 3 times. But in fact, the way that term frequency calculations work is that item number 1 is first, because although it says term frequency only 2 times, it's out of only 8 terms in total. So document number 1 gets a higher term frequency score than document number 3. Also, for the purposes of this exercise, I did not remove stop words. It's just a little easier to count that way, so forgive me for leaving stop words in there. For that reason, these results are going to look really weird. Interesting thing about term frequency is that you can really easily do something called keyword stuffing to become the top result. If I really wanted tweet number 2 to always show up at the top, specifically when someone searches for cat, I would just throw in like cat, 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 and boom, it's all of a sudden number 1. The other form of keyword stuffing that you might have seen out there in the wild involves, rather than trying to become the top results for some particular search, just getting included in as many candidate sets as possible. Like I want to be found in everyone's search for any word. So you've probably seen this when you go to Craigslist or Kijiji or your local buy and sell of choice, and you search for lamp, and you see a couch in the results. And you're like, what the heck? So you click on the couch, and you see at the bottom of the description of the couch, they've gone desk, lamp, table, chair, bed, dresser. Like, they've just named every piece of furniture they could possibly think of. So that's the other form of keyword stuffing, where they're just trying to get found in every candidate set possible. Very annoying. Next, we're going to look at inverse document frequency. And it's going to get a little freaky, so bear with me. We are going to imagine that I have 100 tweets that all say cat in them. Very important. Every single one says cat in it somewhere. I tweet about cats a lot. What can I say? But only these first two have the word orange in them. So this is not real math. This is hand-wavy slide math. But basically, when we score for term frequency and versus document frequency, we score each term in the query independently for each document. The inverse document frequency of cat is 0. Because you see, cat is in every tweet in the entire corpus of tweets. I've never tweeted about something that was not cats. So the score of cat is 0 because it's effectively a stop word. It adds as much value as the or a. So what this means, oh, and then of course the IDF of orange is very high because it's only in 2 out of 100 tweets. So what this means is that we end up basically not counting at all the score of cat, and the only thing that matters and dominates the ranking in TFIDF is the score of the term orange. So this means that since orange is only 1 of the 7 in the first tweet, and it's 1 of 5 in the second tweet comes first. This probably looks wrong to you. There's a couple of reasons for that. First of all, TFIDF is not perfect. Second of all, there's a lot of things we often add on top of TFIDF to make relevance a lot better. And the first one that I'll touch on a little bit is called phrase matching. Let's go back to this last slide. The reason this looked really ridiculous is that we typed in a phrase. We typed orange cat, 2 words, like order 1, 2. Those same 2 words in the same order appeared in tweet number 1. So like, why is that not the top result? And the answer is because we didn't apply any phrase matching. The reason phrase matching is difficult is that when we created our inverted index, we completely sliced and diced the input data into a form such that we cannot recreate the original string. Please do not try to store all of your original data in your search engine. Search engines are not databases. They act like databases, but that's not the way to solve this problem. I'm not going to do some slides on this because it's like super complicated, but basically what happens is while it's tokenizing, your search engine stores some metadata about each token and what position it was in and how long each string was, and then we can use that to do like a best effort at determining whether or not a phrase is in there. So if we added phrase matching, tweet number 1 would come in first place for sure. Other things you might want to add to your relevance algorithm to make it better are fuzzy matching or spelling correction. Sometimes people make typos. Fuzzy matching is really related to the autocomplete or predictive text problem. So can we match when you only typed in part of a string and offer you suggestions when you're not quite done? Again, you can probably see how the inverted index didn't fully solve that problem because we had to do exact string matches on the bucket. The solution involves storing every possible combination of substring of every word in the bucket as well. Tough problem to solve, takes a lot of extra memory, but that's how we do it. Other factors you might want to include in your relevance, and now we're getting into like customization territory, would be things like the user's location. Like we want to boost items that ship from locations near them because shipping will be cheaper and faster. Or maybe we can determine something about the user's language. So if I have a French user that typed in ROSE, can I determine that they were looking for items that are pink, rose, rather than the flower rose? Maybe. Quality is another really common one in the field of e-commerce. So the concept here is that even if there's an item that is like the most relevant by text, I might want to show another item earlier because it's like a bestseller. So you'll see on Amazon, for example, they'll boost bestsellers up to the top. So what they're doing typically is machine learning. They're collecting click data and the items that people are clicking on more, adding to their cart more, fully checking out and buying more. Those end up getting this like quality score that boosts them up in the results. And then finally, just for fun, you could also add elements of recency and randomness. I used to work for Etsy, and Etsy is a big marketplace of like wild handmade items. It's like the Wild West of like crazy handmade stuff. And Etsy intentionally injects a concept of recency and randomness into their search algorithm, so that if you go to Etsy and you search for like purple necklace, and then you go like 2 days later, you get slightly different results, just for fun. Last thing I have to tell you, I'm so sorry, nobody uses TFIDF anymore. The reason I still taught it to you is that the new hotness, which is called BM25, is basically distributed TFIDF. So the concepts that we learned, term frequency and inverse document frequency, are still very important to BM25, but if you want to learn the actual math of how BM25 works, I invite you to check out the Elasticsearch blog on the topic. Finally, speaking of Elasticsearch, if you're thinking, gosh, I could use some better quality, faster text results for my website, you might want to incorporate a search engine. There are two very popular open source search engines. They're called Solr and Elasticsearch. They are both built on top of the same underlying library, which is called Lucene. So Lucene is a library that was written originally in 1999, but it still enjoys a very active open source community today. Solr and Elasticsearch are basically two sides of the same coin. While Lucene implements the actual inverted index that we saw today, and in order to do so, they use some basic versions of tokenization, normalization, and ranking, Solr and Elasticsearch are what you want. They take the Lucene library and they make it into a long-running server that's out of the box, sharded, replicated, distributed, so it can handle huge volumes of data. You can scale it up and down. It accepts HTTP requests, so you don't have to write your code in Java to talk to it. Any language that can talk to something over HTTP can insert and extract information from either Solr or Elasticsearch. They also offer some more advanced versions of tokenization, normalization, and ranking, and perhaps most interestingly, they both have plugin frameworks so that you can try to write your own customizations if you need something like really wild, like say you want to inject recency and randomness. You might write a custom query handler for that. But which one should I pick, Toria? The answer is, it doesn't matter. People who are much smarter than me have tried to prove that one or the other is faster or better across the board or for some specific subset or type of data set. And every time they thought that they proved that one outperformed the other, they found out later they made a configuration error. So, ideally, if you have the time, just test your data set with both and see which one works better with the defaults, because there are a lot of knobs to tune, and even the experts get it wrong sometimes. So most projects work well with either. Just pick one and get started. But also, if you would like a little bit of my personal opinion, I think Solr is the better bet for the plugin framework. I think for advanced levels of customization, if you're pretty sure this is like a long-term bet, you're working for a big company that wants to invest a lot of time in it, you might want to choose Solr because their plugin framework I find a little easier to use. Not easy, but easier than Elasticsearch. But 99% of the time, what you want is Elasticsearch. It is way easier to get up and running for the first time. The documentation is way more accessible. There's way more stuff about Elasticsearch on Stack Overflow. You're going to have a better time trying to use Elasticsearch. In conclusion, we learned that text search is solved using an inverted index inside of search engines. And it is both faster and better than a database in terms of the quality of results it pulls into the candidate set very quickly. After we've retrieved the candidate set of items that are related to the terms we're searching for, we then want to rank them in some order, which is typically relevance order. We use TFIDF, but kind of not. The new hotness is called BM25, but it's just distributed TFIDF. And then finally, we learned that Solr and Elasticsearch are the two by far and away most popular and best open source search engines. And if you want text search for your project, you want one of those. Thank you very much.